Out in open water, bringing a 300-meter merchant vessel to a halt to drop its anchor is a massive physical event. To a passenger on a cruise ship, dropping anchor feels like parking a car. But to a master mariner, the ship has actually entered a highly precarious state of physical tension. Though the hull appears stationary, it is constantly battered by invisible vectors. Wind, tide, and subsurface currents are continuously pushing against thousands of tons of steel. The primary objective for the officer of the watch is to ensure that the mechanical holding power of the anchor dug into the seabed constantly exceeds these incoming impulse forces. If those environmental forces win, the anchor loses its grip on the bottom. The entire bridge crew is guarding against this exact failure state, known as dragging. The anchor watch demands the active, continuous management of physics to prevent a multi-million-dollar asset from drifting into disaster. A fully loaded merchant vessel possesses immense mass and inertia. If it begins to drift out of control, stopping it is incredibly difficult and eats up critical time. Avoiding a catastrophic grounding or a collision with nearby vessels relies entirely on early detection of that initial movement. But here is the primary complication. An anchored ship is supposed to move. As winds and tides shift, the vessel continuously pivots and swings around the exact point where the anchor was dropped. How does the officer of the watch distinguish between a natural, safe swing and a dangerous, uncontrolled drag? Human intuition is useless in the dark or in thick fog. To separate safe movement from a failure of the anchor, the officer must rely on a strict, mathematically defined geographic envelope. To map out this operational space, we have to look at the vessel and the anchor from a top-down geographic perspective. This boundary is known as the turning circle, or swing circle. It represents the maximum geometric path traced by the ship's pivot point as it executes a complete turn from one side to the other. The size of this circle is dictated by a few fixed variables: the sheer length of the vessel itself and the hull's underwater profile, which determines how much water resistance the ship generates. Then there is the primary adjustable variable, the length of the anchor cable paid out, which mariners measure in units called shackles. This formula provides the precise turning circle radius. By taking the number of shackles, say 6, multiplying by 27.5 meters, and adding the ship's length, the crew determines the total radius. Dividing by 1852 converts the safety boundary into nautical miles. Determining exactly how many shackles to use is a strategic decision. A longer cable allows the vessel to swing in a wider, safer arc, reducing the risk of dragging in strong currents, but it physically places the ship closer to surrounding hazards. Once calculated, the ship effectively traces this boundary on the nautical chart as it pivots with the shifting tide. Wind and current push the vessel until it rests at the very edge of this calculated boundary, holding the heady anchor chain in tension. Drawing this specific circle on the chart is the most critical task for the officer of the watch. It establishes the absolute binary boundary between safety and failure. Inside the bridge, the officer of the watch relies on an array of specific instruments to monitor the vessel's position against that calculated geometry in real time. This radar display allows for continuous monitoring. By measuring the distance to fixed coastal objects or changing seabed topography, the officer can detect any unusual swing patterns. They also employ manual techniques, like taking regular beam bearings on fixed lighthouses or buoys. If the bearing of a fixed object changes rapidly, the ship is swinging off its anchor and beginning to drag. The most precise monitoring tool at their disposal is the combination of the Doppler log and the course recorder. A ship safely swinging on its anchor acts like a massive pendulum. As it moves back and forth with the tide, it naturally creates a rhythmic, highly predictable data pattern. This course recorder output captures that pendular motion, tracing a regular sine curve. But when the anchor loses its grip, the pattern breaks. The curve immediately becomes distorted and jagged, reflecting the physical chaos below the waterline. This is quickly confirmed by other instruments. The Doppler log will suddenly indicate a speed exceeding 1 knot in a specific direction, while the echo sounder may show depth readings dropping as the ship moves into shallower water. A dragging anchor is rarely felt by the crew in the bridge. It is diagnosed entirely through the sudden, terrifying distortion of rhythmic instrumental data. Beyond internal monitoring, international law requires the vessel to clearly broadcast its immobilized state to surrounding marine traffic. Under regulations, an anchored vessel must exhibit a specific shape during the daytime, a single black ball hoisted in the forepart. At night, this changes to all-round white lights, indicating the vessel's presence and massive length to other mariners. But in restricted visibility conditions, like thick fog, visual shapes and lights are rendered useless. To establish presence, the ship must deploy mandatory sound signals, ringing the ship's bell rapidly for 5 seconds at intervals of not more than 1 minute. For massive vessels over 100 meters, there is a secondary requirement. Immediately after the ringing of the bell, a gong must be sounded in the aft part of the ship. Strict adherence to Rule 30 is a liability shield. It legally establishes the anchored vessel's right to that specific radius of ocean, transferring the responsibility of avoidance to all moving traffic. The alarms have sounded, the sine curve is distorted, and the vessel has breached the boundary of its calculated swing circle. The anchor is dragging. Up on the bow, the physical reality is violent. The massive steel anchor chain jerks taut, then goes ominously slack as the anchor violently loses and regains purchase on the seabed, shaking the machinery. The master has immediate kinetic options to regain control. The fastest response is paying out more cable, slipping it further into the water to increase distance and drag friction. If space permits, a secondary option is using the main engines boldly. The crew can steam ahead, forcefully dredging the anchor and chain back into a secure holding position. But there is an ultimate worst-case scenario. The vessel is dragging directly into a busy shipping lane or towards another anchored ship, and a collision is imminent. The extreme emergency protocol is slipping the cable entirely from the bitter end. The crew abandons the anchor, instantly freeing the ship to execute evasive maneuvers. In extremis, losing the anchor and chain is vastly cheaper than a hull breach. Survival requires immediate, decisive sacrifice. Once the crisis is averted and the ship is securely re-anchored, the aftermath shifts immediately from physical survival to legal defense. The deck logbook serves as the ship's immutable memory. It is the primary legal document demanded by investigators after any incident. The officer of the watch is mandated to record highly specific data points throughout the watch. This includes exact GPS coordinates, detailed weather observations, times of course alterations, and exact engine standby times. This handwritten data is not administrative busywork. It allows authorities to flawlessly reconstruct the passage and prove whether the crew acted reasonably under the conditions. The procedural rigidity of this document is absolute. Entries must be continuous and written only in pen. Mistakes can never be overwritten. They must be struck through once, corrected, and initialed at the side. The watch reaches its final completion when the mathematical proof of that grip is permanently inked in the logbook. Safety at sea relies on the rigorous application of physics, secured by meticulous documentation.